Hi, I'm Daisy Thornton. I'm a PhD researcher at Imperial College London, working on the Degradation project, and I'll be speaking briefly about my PhD project, which is probing degradation in lithium ion batteries with on-chip electrochemistry mass spectrometry. So many of the key degradation mechanisms that contribute to declining electrochemical performance in lithium ion batteries are accompanied by some form of gas evolution. So, for example, the decomposition of the electrolyte at the cathode to form the cathode-electrolyte interface is often accompanied by carbon dioxide evolution. Similarly, phase transitions on the surface of an NMC811 particle to the spinel phase or to the rock salt phase is often accompanied by oxygen evolution. So we can see how being able to measure this gas evolution as a function of electrochemical cycling can provide valuable mechanistic insight into these parasitic processes. And this is exactly what we can do with electrochemistry mass spectrometry. So throughout my project, I've collaborated with Spectro Inlets, which is a company that have developed a new type of electrochemistry mass spectrometry called on-chip electrochemistry mass spectrometry. So the technique employs a microfabricated membrane chip to create a well-defined interface between the vacuum environment of a mass spectrometer and the liquid environment of an electrochemical cell. The chip then precisely controls the fast and lossless transfer of the volatile species from the electrochemical cell to be measured by the mass spec. The technique was originally developed for use in aqueous electrochemistry, and so throughout my project we've been working on developing it further for use in non-aqueous electrochemical systems such as lithium ion batteries. So part of the work that was required for this development was the design of a new electrochemical cell, and here's what we came up with. So here's the conceptual drawing of the cell, which shows how we use a mesh current collector for the working electrode to enable the volatile species that are evolved in the system to be collected by the membrane. So the cell design facilitates the fast and lossless transfer of the volatile species from the working electrode to the mass spectrometer, and it enables us to have new real-time insight into lithium ion battery degradation mechanisms with unprecedented sensitivity. Also, interestingly, this work led to a collaboration with Johnson Matthey, who also purchased this instrument, and this work is funded by the Royce Institute. An example of the type of data that we can collect with the technique is shown here. So here we perform cyclic voltammetry on a graphite versus lithium cell, and we can see that as the potential lowers towards 0 volts versus lithium, we can see the onset of ethylene evolution. This ethylene evolution is likely a product of the decomposition of the ethylene carbonate component of the electrolyte, which also forms the SCI components such as LEDC and lithium carbonate, as shown by these reactions at the top here. So using this ethylene evolution as an indicator of SCI formation and growth, we can investigate how different factors might influence SCI growth as a function of electrochemical cycling. So for example, we're quite interested in understanding how transition metals that are dissolved from the cathode might cross over to the anode and catalyze further SCI growth. So we're hoping to correlate our findings with other surface analysis measurements such as XPS and SIMS performed by other members of the Degradation project, and this will enable us to gain a holistic understanding of the complex and interlinking degradation mechanisms that take place in NMC811 based lithium ion batteries. Thanks so much for listening, and if you have any questions, please feel free to get in touch with me or any of my supervisors.